Hello everyone, welcome back to Strong Compute's 3D Compute Manager. We have two new features to show you today, which are storage and scheduling. So in terms of storage, the CM now has the notion of storage on clusters. It will aggregate the amount of storage that your cluster has. In this case, this has a very, very small pool of 100 gigabytes just for this example. And when you go ahead and cache datasets, it will take up an amount of storage on the cluster. And if you have too many, it will not let you cache them. So clusters will have a maximum amount of storage you're allowed to have, which is how it works in real life. You can't just have as many as you want. And yeah, if you try and cache to any cluster that has enough storage, you can just do as many as you want, like that. And this one has 256 TB bytes. So we're not going to be using any of that up anytime soon. The other thing that we've got going on is in case you lose a node or add a node into your cluster, the cluster is going to start resilvering, which means it has to reformat some of the data on your drive to rearrange it based on the parity so you don't lose anything. Your jobs can still run while the cluster is doing this. It's just going to run slower because of the compute power that it's using.
Yeah, so what's happening behind the scenes here is the strong compute systems, the agents on the nodes, and the control plane are building a Ceph array out of the drives that you have on your node. So you go and adopt, in this case, 8 nodes into this this cluster here, and we're firing up Ceph, and we're diagnosing how many drives are in the nodes. We're bringing them together into a pool with Ceph with some level of erasure code, which is the parity system in Ceph. And that's making it so that if you lose a node, you're not going to lose your data, depending on the level of erasure code that you've applied. And the resilvering is when you lose a node or you add some nodes and you want to restore that level of erasure code or maintain that level of erasure code. Things will need to kind of move around the machines a bit to facilitate that. And that's normally quite difficult and painful to organize. Not only have we organized it, we've automated it. So yeah, that makes life a lot easier on the ops side of things. And then we make available, to the manager, the ops people, and the engineers using those volumes, which are there for pulling in data sets, for putting checkpoints to, that sort of thing.
That's what this is.
And so, yeah, you can see that big bar there that Xander's put on the interface, which shows you how much storage you have available on your cluster. Obviously, as clusters get larger, there'll be different pools and things like that. But that will come all a little bit later. But yeah, the important thing here is that you're getting like real clustered storage without having to do that work, which is nice. And we can see what it's doing, and we can bring data sets in. Will the jobs auto cache their
they sure do, yeah. If we go ahead and add some, like a space that we can run jobs on, and we go try and cache or create a job that uses data sets, it's actually going to wait for those data sets to cache, and then as soon as they're ready, it would jump in. But because this one won't fit on the cluster, it's not going to start the job until it has room. So in case we need to, we can drag this over to, a cluster that has space. This one's already got those data sets cached, so it is just going to go ahead and start
running.
Yeah. So they'll be pending. They'll be in a download pending state until the resources they need are ready. Right now, they are the data set caches. You also need to grab the snapshots of your container, which is not a notion that exists in the CM right now. But they're the things that your job kind of waits for before it can actually jump in the queue.
Cool. All right. So we're getting closer and closer to one-to-one with our real systems.
Yeah. And talking one-to-one with our systems, the scheduler algorithm that the CM uses is, I'm pretty sure at this point, one-to-one with the real business logic. So as we could see here while we were talking, we have some jobs here that are properly cycling. These are interruptible jobs. So in this case,
it might be worth just talking about the 3 main types of jobs that we have. So we've got dedicated jobs that run in a dedicated space just until they're done.
Yeah, like this one over here.
This one over here. So it'll just run until it's done. There can be more backed up in the queue until one of them's finished. There won't be space for the next one to come on. We realized that this is how a lot of traditional workload schedulers run, like Slurm. And there can be some good bin packing algorithms to try to maximize utilization of the cluster. But there's a couple of problems. If you want to just see some progress on a whole bunch of jobs, it's going to be really hard to do that because they're going to need to move through the queue. And the other problem is that if you've got a big job that needs a lot of nodes, the bin packer is going to keep taking the jobs that have been in the queue less time that are smaller and keep squeezing them in to the space. And so your big job is never going to run. And so that is why we created the notion of time cycled spaces. And so this is where before a job completes, it will actually get off the cluster and go back into the queue, allowing another job to come on. And those jobs are going to move through in sequence. So even if it's a large job, it's still definitely going to get some time on the cluster. So that can be great when you're GPU constrained and you don't have the ability to go and access additional GPUs because you don't have budget for that. But that still leaves another problem, which is what if you don't know if you actually want to run a job for hours or days. You just want to try and see if the job works. And so we probably need to do a little bit of work on the naming here, but the jobs where you can just test them very quickly are called cycle jobs in our system. And so here we've got a couple of interruptible jobs. So these are effectively the lowest priority jobs in our system. They're always going to make a little bit of progress, but they are rapidly going to make way for any kind of these urgent test jobs that we call cycling jobs.
Let's chuck one up. So if you have like this urgent job that you really need to run, it's going to kick the interruptible ones off while it does its thing. And they're going to cycle in their own queue. So all the interruptible jobs are just going to wait, and the cycle jobs are going to cycle in like 90-second increments. They're there for the rapid testing, like you said.
Yeah, and the reason we call them cycle jobs rather than rapid or test or urgent or something is because what we're explicitly trying to test here is that the job can make progress when it's being allowed on the cluster and then getting booted off the cluster and then coming back onto the cluster again. So what we're really testing here is the cycling or the integration of our cycling utils, which is the state saving. And this is what enables jobs to rotate with each other as interruptible jobs. It enables jobs to pause and move to another cluster and resume because we're doing that state saving. It enables jobs to recover if there's a hardware failure. So, and we're also just sort of testing that some progress actually gets made in this job. So whatever the experimental kind of objective that you're trying to achieve here, we're testing that you're actually going to actually make some of that progress, and that you're going to save state.
It's worth noting that for these cycle jobs that you kind of use for your quick testing, these ones are not ones you can pick up and drag. Those are for interruptible, which means these interruptible jobs, if you really need them to run, these are the ones you'll drag over to other places. These are the ones you can burst out to other clusters. It's somewhere in the world. These cycle ones will stay until they're done or until you boot them off. The interruptible ones are the ones that will kind of last longer. They're the ones that are
and so it's probably worth mentioning a bit about the timing this stuff takes as well. So we've sort of sped things up a little bit in the simulator. On a real cluster, your interruptible jobs can launch in as little as like 10 or 15 seconds. So it's your cycle jobs, and your interruptible jobs if the cluster's empty, can launch in as little as 10 or 15 seconds, which is really great for testing at cluster scale because you normally don't have on-demand access to massive clusters. They're too expensive. So this solves that problem. When it comes to migrating clusters, spinning up burst regions and things like that, you're looking at more 5, 10, 15 minutes in the real world for that to happen. And that's why having that really rapid cycling testing ability is so critical, because as an engineer, you don't want to be sitting there waiting 15 minutes to get some feedback if the last line of code you put in is functional or not.
Yeah. All right. Well, that's this week's update. Thank you.
Well, thank you, Xander.